Ultrasonic detection is one of the greatest ways of reliably sensing levels and determining proximity. Since they have been in use for many years, ultrasonic sensors have a significant portion of the sensing market. These sensors play a crucial role in countless applications, from industrial automation to robotics and automotive safety systems. In this brief overview, we'll delve into the mechanics of ultrasonic sensor working. The use of ultrasonic sensors in various fields, such as drones and electric cars, is growing as the automation sector develops. Driven by the need for safety, advancements in offerings, and surging demand for sensor-based networks, Allied Market Research projects the smart office market to reach $90 billion by 2030. Due to increased energy efficiency to support industry and local regulations, ultrasonic sensors are playing an expanded role in automating various processes around the office. A prime example of this is HVAC and lighting control. Ultrasonic sensors have been employed to detect populated rooms in the office throughout the day. HVAC systems can be programmed, using this data, to heat or cool rooms that are in use or turn off the systems at night and kick back on upon first arrival. This blog provides a deep knowledge of what is ultrasonic sensor and how it works. Ultrasonic sensors are electronic devices that determine a target's distance. They work by emitting ultrasonic sound waves and converting those waves into electrical signals. Furthermore, ultrasonic travel at a faster rate than audible sounds. Therefore, ultrasonic sensor work involves sound waves to find the distance to an item. A transducer is also there to transmit and receive ultrasonic pulses. These pulses help to communicate information about an object within range. Further, this detail can be applied in various applications including industrial. The sensor's transducer serves as a microphone to receive and transmit ultrasonic sound. They also use a single transducer to send and receive pulses. Further, the sensor measures the total time taken to deliver and receive an ultrasonic pulse and calculates the target's distance. The working principle of an ultrasonic sensor revolves around the emission and reception of high-frequency sound waves. These waves range from 20 kHz, which is beyond the range of human hearing. An ultrasonic distance sensor detects objects in a contactless manner and measures the distance between the sensor and the measured object. To do this, it cyclically emits a short, high-frequency sound wave at the sensor head. This travels through the air at the speed of sound. If the sonic pulse encounters an object, this object reflects it back to the ultrasonic sensor. The ultrasonic probe then internally calculates the distance to the target object by measuring the time between the emission and reception of the sonic pulse. At the heart of an ultrasonic sensor's operation lies a simple yet ingenious principle: how a sound wave takes the time to reach an object and return. The radar can determine the object's position by measuring this time interval and the speed of the traveling medium, typically the air. However, the radar can only determine this with an error of several feet from its actual position. This formula makes the ultrasonic sensor highly accurate. It determines the distance by measuring the time it takes for sound waves to travel. Speed of sound, constantly known, is a material's sound speed. Under dry air at room temperature, 68 degrees Fahrenheit or 20 degrees Celsius, the atmospheric sky sound speed is approximately 343 meters per second. This is equivalent to 1,125 feet per second. Time. The sensor uses time definition to receive ultrasonic waves, travel to the object, and return, and it normally measures in microseconds. Multiplication by speed of sound. The actual time is multiplied by the speed to determine the overall distance where the sound wave is propagated. Division by 2, thus, the sound wave divides the quantity of the distance by 2 as it travels to the object and then back, leaving the accurate distance to the object. Although ultrasonic sensors share the same working principle, they are classified into multiple types based on their design, characteristics, and applications. Here are some common types of ultrasonic sensors. Single-point sensors. These sensors pinpoint the distance to any one point or object within their ultrasonic sensor range of vision. Most are used for proximity detection and distance measurement, especially in simple tasks. Array sensors. The sensor array comprises several transducer elements organized in a specific array pattern. This configuration allows for measurements in multiple directions or creating three-dimensional environmental models. Additionally, these elements can be arranged in a specific array pattern, facilitating multiple direction measurements or three-dimensional environmental modeling. Proximity switches. These devices use ultrasonic waves to detect objects. They integrate both the transmitter and receiver. The ultrasound is reflected directly back to the receiver from the object to measure distance. Furthermore, the transmitter emits ultrasonic waves while the receiver detects the waves reflected off objects. Retroreflective sensors. Retroreflective sensors are designed to detect objects based on the reflection principle. These sensors emit a beam of light, typically infrared, towards a reflector opposite them. When an object interrupts this beam by passing between the sensor and the reflector, the sensor detects the object's presence. Through-beam sensors. Unlike through-beam sensors, which have independent sender and receiver units, each one is responsible for sending and receiving the specified ultrasonic waves that travel through the air or some other medium to get to the receiving unit. The sonic cone determines the area within which objects can be reliably detected by ultrasonic sensors. What is an aperture angle? Parameter alpha defines the aperture angle of the cone-shaped sonic cone emitted by the ultrasonic sensor. The surface structure of the measured object has no influence on the measurement result. This means uneven bulk materials, punched sheets with holes, or moving and bouncing objects can be detected. Thus, for uneven surfaces, the aperture angle is set particularly wide, while for narrow and small surfaces, it is set particularly narrow. To allow the ultrasonic sensor to measure the time between the transmitted and received signal, the object to be detected must reflect enough sound. The smaller the target surface area, the smaller the amount of sound reflected. If the object is too small, not enough sound can be reflected, which means the sensor can no longer detect the target. Therefore, sensors with a narrow sonic cone should be used for measuring small objects. Thanks to the focus sound beam, a large portion of the sonic energy then directly hits the object. As a result, almost the entire sonic energy can be reproduced by the target and perceived by the sensor. In general, it is not a problem if the target is smaller than the sonic cone. For the switching point, the sensor focuses on the earliest object it can detect. The ultrasonic waves can be deflected by another object. This object must have a hard flat surface that relays the signal well. Care should be taken to ensure that only one deflection is used, as multiple deflections result in a significant decrease in sound wave range. To ensure that no large debris falls onto the active surface, a baffle plate can be used. In an ultrasonic sensor, the sensor surface on which the sound signal is generated is referred to as an oscillator, active surface, ceramic converter, or transducer. Since this surface vibrates, the sensor is resistant to contamination to a certain degree. Dirt and grime do not stick to the oscillator, but instead are blown away by the fine movements. Excellent background suppression. Since the distance is determined by ultrasound waves, the background in front of which the object is located is almost irrelevant. Detection of almost all materials. Any material that reflects sound is detected. However, hard material reflects the impulse energy particularly well. Colors, shapes, or transparency do not play a role. In addition to wood, plastic, and metal, thin films or glass can also be detected. Wide range of distances. Ultrasonic sensors detect objects in the immediate vicinity, 3 centimeters, as well as those up to nearly 6 meters away. Resistant to interfering influences. Dirt, mist, and dust have almost no effect on the sensor's function. Ultrasonic sensors also do not produce or require light to operate, making them well suited for applications in variable light conditions. With high refresh rates, hundreds of chirps per second, relatively small footprints, and lower cost compared with other technologies, such as photoelectric, laser, and inductive sensors, it becomes easy to see why ultrasonic sensors are so established. Soft material like cotton, fabrics, foam rubber, or felt absorb the sound or diffusely reflect the sound. As a result, an ultrasonic sensor passes through the soft material and the hard surface, e.g. the table behind it, is detected instead. Objects with an extremely high temperature result in the echo only reaching the sensor head diffusely or not at all. Environmental factors such as air turbulence can have an impact on echo quality and therefore also the measurements. The ambient temperature influence is cancelled by temperature compensation. This image illustrates the optimal installation of an ultrasonic sensor. The angle can be larger for most object surfaces. Possible uses for ultrasonic sensors.